Good evening. Welcome to the live interaction session for fourth week of our course Computational Fluid Dynamics by Professor Srinivas Jayanti, Department of Chemical Engineering, IIT Madras. Myself, Manchunathan, PhD scholar, the Department of Applied Mechanics, IIT Madras. So, in week 4 of our lectures, of our course, the equations of the governing equations regarding mostly governing equations for incompressible flows, including uh, energy equation and also some insights on species transport equation. All this have been discussed together along with their boundary conditions. So these particular equations will be discretized to established in the CFD of the respective problems. So let's move on to our session. So first question is on for a 2D incompressible flow of air containing water vapor, what are the boundary conditions needed for the water vapor transport equation? So you can inbox your answers. This is supposed to be an interactive session. Please inbox the answers. So the question is, for a 2D incompressible flow of air containing water vapor, what are the boundary conditions needed for water vapor transport equation? Options are A. Inlet mass fraction, outlet pressure, and no slip walls. Option B. Inlet velocity, outlet mass fraction, no slip walls. Option C. Inlet and outlet mass fractions and no slip walls. Option D. Inlet velocity, outlet pressure, and specified mass fluxes on walls. You can inbox your answers. So the first question is, for a 2D incompressible flow of air containing water vapor, what are the boundary conditions needed for the water vapor transport equation? Options are inlet mass fraction, outlet pressure, and no slip walls. Option B, inlet velocity, outlet mass fraction and no slip walls. Option C, inlet and outlet mass fractions and no slip walls. Option D, inlet velocity, outlet pressure, and specified mass fluxes on walls. You can inbox your answers. So this is a question on species transport. So, the question is on species transport. So here, water vapor. So water as well as water in uh, air and water vapor mixture is there. So there is two species. So this type of problems are called species transfer problems. Transfer problems. So mostly in our CFD of single species or simple fluid flow, our inlet velocity, and uh, inlet velocity and outlet condition may be pressure or gradient of velocity, and now slip walls will be given. But here, this since this is a species transfer, there it contains more than one species. So there, the mass fractions are uh, in particular role for the transport. So among the this option D, inlet velocity, outlet pressure, and mass fluxes on walls will be needed to solve our first question. So for species transport equations, species transport problems, the concentrations will be needed in the inlet and outlet along with the velocity of convection. So our option is option D for the first question. Moving on to second question. What are the key challenges in simulating complex chemical reaction mechanisms in CFD? So it's a simple question. What are the key challenges in simulating complex chemical reactions in CFD? Option A large number of species and reaction. Option B, stiffness of reaction rates. Option C, accurate turbulence modeling. Option D, all of the above. You can inbox your answers. Our answer is option D, all of the above. As you can see, we may have, you may know me. Mostly chemical reaction will be in some comments. I'm just writing it for simplified. A plus B gives some C plus D kind of reactions. But here, all this A will be some elements. Suppose here, if you are taking methane, then there will be carbon, hydrogen, and all. Then suppose this is, if it is oxygen, then there itself became three uh, species, and the reactions will be there, and also the reaction level will be changing. Give me a sec. Yes, so there will be a lot of species or types of molecules involved in it, and that species will have their own properties. So integrating all these equation, and how these equation, suppose this is one particular chemical equation, and how it will affect the mass flow. Since we know in our uh, CFD, what we are dealing with is the density and velocity for mass flow rate. So these kind of mass flow rates, these kind of species should be written in terms of concentrations and density, which will in turn make the modeling difficult, and also it will increase the computational cost. Whereas also this stiffness of reaction rates, all these kind of things will require a lot of better integration methods. How these uh, we know when we have more than one equation, we have to integrate it. Sorry, we have to uh, couple it. All the effect of the physics should be included. And when the number of variables are more, we will have to add more equations and solve them to get a closure problem. And also some chemical reaction as such in combustion and all, we have to model turbulence also. So all the above are challenges faced during chemical reaction CFD. So our answer is option D, because these factors will contribute to increasing computational cost and complexity, and requires efficient integration method as number of equation will as the physics become complex, the number of equations will increase, and also when the variables number of variables increase, we will have to add more models. And also when these chemical reactions have turbulent nature, then turbulent mixing effects should be also considered for solving the CFD problems. Moving on to next question. Which of the following terms is not included in the general form of the species conservation equation? Hope you have all have gone through the fourth week lecture videos. So in the fourth week lecture videos, the general form of species conservation equation is discussed. So which of the following terms are not included in the general form of species conservation equation? Option A, conservation convection time. Option B, diffusion time. Option C, source time. Option D, pressure time. You can inbox your answers. Which among the following is not included or not present in the general species conservation equation? The answer is option D, pressure time. Since as we have already discussed in the previous question, the pressure time is not directly involved in uh, species transfer, but it can influence the concentration and thereby indirectly influence the fluid flow. So our answer is option D, pressure time. Moving on to next question. The diffusion coefficient in species conservation equation represent which among the following? Options are the rate of chemical reaction. Option B, the resistance to species movement due to concentration gradients. Option C, the bulk movement of species by the fluid flow. Option D, the effect of pressure on species concentration. Option E, total mass of the species in the system. So, what does the diffusion coefficient in the species conservation equation represent? Answer is option B, resistance to species movement due to concentration gradients. Actually, the diffusion coefficient is written as given by D and is taken as negative D. So it's a resistance. D gives the uh, uh, diffusion with the concentration gradient, and negative D shows the resistance of species movement due to concentration gradient. Option B is our answer. Moving on to next question. Consider a CFD simulation of combustion in a reactor. Which of the following boundary condition is most likely used for species concentration at the inlet? So, in the case of a combustion reaction, which of the following boundary condition is most likely used for the species concentration at the inlet? Option A, zero gradient. Option B, fixed value. Option C, mass flow rate. Option D, user defined function. Option E, pressure outlet. So the question is on what will be the boundary condition for species concentration at inlet for a combustion in a reactor. You can inbox your answers. Our answer is option B, fixed value. So it's like there is a boundary condition for species concentration. So since it's a concentration, zero gradient cannot be applied in the inlet. Also, mass flow rate is given to the inlet mass flow. The species concentration is how much, what's the ratio of species, the different types of species in the inflow. So UDF itself is not a boundary condition. It's like how we implement a boundary condition. This again, pressure is for outlet. So all the other options are wrong. Our right answer is fixed value. And also it is typically fixed specified as fixed value, and it can change in rare conditions depending on the combustion process. Moving on to next question. In a numerical solution of the species conservation equation, the discretization method commonly used is. So the question is on the discretization method commonly used for solving species conservation equation. Options are A, direct integration. Option B, finite difference method or FDF. Option C, finite element method or FEM. Option D, finite volume method or FVM. Option E, Monte Carlo method. So which among the following is commonly used for discretizing the species conservation equation? Direct integration is way of combining equations, not discretizing method. And among the discretizing, these three are the discretizing method, commonly followed discretization method, and among them, finite volume method or FVM, that is option D, is commonly used for solving species conservation equation. And Monte Carlo method is something that is used for predicting probability of variation when the input parameters have a variation range, how much the output uh, parameters can vary. Such kind of a probability simulation method is called Monte Carlo method, which is not a discretization method at all. Our answer is option D, finite volume method. Moving on to next question. A CFT simulation predicts a negative concentration for a species. What is the most likely explanation? So, when solving a CFD simulation with species transport, a negative concentration gradient is predicted for a species. What is the most likely explanation? Option A, numerical error due to discretization. Option B, incorrect boundary condition. Option C, presence of a sink term for the species. Option D, violation of the laws of thermodynamics. Option E, insufficient mesh resolution. So, among the following, many options can be the reason, but which is the most likely explanation? So our answer is option A, numerical error due to discretization. The question is on most likely explanation. If you see, numerical error due to discretization can lead to a negative concentration gradient. And then, so if you are to check where the simulation got wrong or where the issue arises, first we have to check from discretization and thing. So if inside the discretization itself there is issue, uh, then it can occur. If not, check the boundary condition. Incorrect boundary condition also give a negative pressure concentration gradient, but most of the time, incorrect boundary condition may not run the simulation. And again, the presence of sync times can be understood by checking discretization methods. So, how sync times are em- deployed in the discretization schemes can be understood from uh, checking discretization. So this is the option C is a subset of option A, and option D is not related. Option E, insufficient mesh resolution, won't may not give negative concentration, it can give other numerical errors. So our answer is option A, numerical error due to discretization. Moving on to next question. What is the primary advantage of using CFD simulation for studying chemical species, transport, and reactions? So the question on what is the advantage of CFD for studying chemical species, transport, and reactions? Options are high accuracy and detailed results. Option B, ability to conduct experiments in dangerous environments. Option C, cost effective compared to physical experiments. Option D, all of the above. Option E, none of the above. You can inbox your answers. If you think uh, from the standpoint of what are the advantages of CFD itself, then it will be easy to answer the question. So let's check our options. So high accuracy and detailed results are not a forte of CFD simulations. CFD simulations, the accuracy is often uh, a choice of the doer. So uh, we can only expect a reasonable uh, accuracy, not high accuracy from CFD simulations. So high accuracy won't be there for CFD simulations. There will only be reasonable accuracy, and that too comes out of the degree of tolerance that we are opting. So the accuracy will be from detail. I mean degree of tolerance that we are choosing. From that only then even then we are only getting reasonable accuracy, and detailed results we will be always we will be integrating for pressure, velocity, and some basic flow properties, and from there we will be deriving other properties and other results. So detailed results is debatable, but high accuracy this term itself makes the option wrong. And moving to next uh, option, ability to conduct experiments in dangerous environments. So this one is true because we can uh, create or experiment with dangerous chemicals and species with a CFD without mm, spending much and also being safe. So CFD is another important feature of CFD is that CFD gives a safe and clean environment for experiments. That's why CFD is also called numerical experiment. So option is uh, answer is option B, ability to conduct experiment in dangerous environments. Which, if you want to do physical experiments, may become unsafe or uh, costly. Option C is also true, cost effective compared to physical experiments. Or CFD can be cost effective. Option D is wrong, since option A is not true. D cannot be true. Option E also cannot be true. So option B is our answer. C can also take an answer, but B and C can be considered as answers. B can also be our answer, since we can dangerous environment as if the chemical, suppose we want to simulate anything in a petroleum rig or something, that kind of things can be simulated using CFD. So yeah, you add B and C. Moving to next question. In chemical species conservation equation, what does the convection term represent? So we have already discussed about diffusion term. So the next question is on, in chemical species conservation equation, what does the convection term represent? Options are option A, rate of mass accumulation due to chemical reaction within the control volume. Option B, rate of mass transfer due to species concentration gradients. Option C, rate of mass diffusion caused by thermal conductivity. Option D, rate of mass transfer across boundaries due to pressure differences. So in CFD, what does the convection term represent? The convection means how something is convected. In normal CFD, how our velocity u is convecting uh, any other property. So if it is heat or something, then how uh, and fluid velocity is convecting heat. So that is what the convection term represents. So uh, in relation to that, if you think, our answer is option B, rate of mass transfer due to species concentration gradients. So here the mass transport will occur or vary with according to the concentration gradients. So as in normal CFD, how the velocity of the flow carries the our transport property, or our property is being transported by the velocity or flow velocity. Here in species transport equation, how the fluid flow is carries the species with it in changing the concentration at specific regions. Moving on to next question. What factor primarily influence the diffusion coefficient in species conservation equation for ideal gas mixtures? So the next question is on diffusion coefficient of ideal gas mixtures. So which of the following factors primarily influences the diffusion coefficient in the species conservation equation of ideal gas mixtures? Options are A. Species viscosity, option B. Temperature of the fluid, option C. Molecular weight of the species, option D. Pressure of the fluid. You can invoke your answers. So we have already discussed what is diffusion coefficient. So diffusion coefficient is mostly in depends on how the species transferred moves, or the resistance offered by the concentration gradient for the movement of particles, a movement of species. So in accordance to that, if you compare, then you can easily get our answer is option C, molecular weight of the species. So concentration gradient and how much uh, For particularly for ideal gas mixtures, this has a relation. For ideal gas mixtures, the diffusion coefficient is inversely proportional to the square root of species molecular weight. And this is related by one particular relation called Stokes-Einstein relation, and which means lighter species, that is, which has lower molecular weight, will diffuse faster, and also the diameter of the molecules is dependent on this. So our answer is option C, molecular weight of the species. Moving on to next question. When specifying the Dirichlet boundary condition for a species in CFD simulation, what information is provided at the boundary phase? So suppose if we are giving a Dirichlet boundary condition for a species, then how what information will be provided at the boundary phase? Options are option A, the species mass flux across the boundary. Option B, the species concentration gradient at the boundary. Option C, the total mass flow rate at the boundary. Option D, the species concentration value at the boundary. Similar question was also discussed before. Our answer is option D, a species concentration gradient. So if you see all other uh, options talks about some gradient or change. So this is a mass flux change value. Concentration gradient is not a Dirichlet boundary condition. So only thing is like concentration value, how one particular value, if we are assigning some phi is equal to constant at the entry, such kind of boundary conditions are called Dirichlet boundary conditions. So option D, the species concentration value at the boundary, is the Dirichlet boundary condition we can prescribe for species concentration at the boundary. Moving on to next question. Next question is on energy balance equation. What does the viscous dissipation term in the energy balance equation represent? Options are option A, heat generation due to internal friction within the fluid. Option B, heat transfer due to radiation exchange with surroundings. Option C, work done on the fluid by external forces. Option D, heat loss due to conduction through boundaries. Which of the following options represent the viscous dissipation time in the energy balance equation? Our answer is option A, heat generation due to internal friction within the fluid. So normally viscous dissipation gives our normally viscous dissipation in fluid flow, general fluid flow, gives the loss of momentum or moment velocity reduction or the friction, uh, the energy dissipated or the loss of momentum occurring due to internal friction of fluid layers. So when in case of energy balance equation, it is uh, uh, it is showing the heat generation due to the internal friction between the layers of the fluid. Our option is option A, heat generation due to internal friction within the fluid. Moving on to next question. The energy balance equation in CFD considers which of the following energy transfer mechanisms? So the question is on what are the energy transfer mechanisms considered in energy balance equation of CFD. Options are option A, convection only, option B, conduction only, option C, convection, conduction and radiation, option D, convection and viscous dissipation only. Which of the following energy transfer mechanisms are considered in energy balance equation of CFD? You can inbox your answers. So our energy balance equation in CFT captures all the three modes of heat transfer or energy transfer, that is convection, conduction and radiation. So our answer is option C. So in convection, uh, how thermal energy is transferred through conduction plus convection. The term convection is from conduction plus advection. And how conduction, how between two neighboring points, how uh, the energy is transferred between two near points, and how it is radiated in terms of electromagnetic waves. So all these three forms of energy transfer is mm, uh, captured in our energy balance equation in CFT. Next question. In energy balance equation, what does specific heat capacity CP represent? So it's a general question. Uh, what does the specific heat capacity represent? Options are total energy content of substance per unit mass. Option B, amount of energy required to raise the temperature of a unit mass by 1 degree. Option C, rate of heat transfer between two substances. Option D, thermal conductivity of a material. So, simple and basic question. What does the term specific heat capacity in energy balance equation represent? Our answer is option B. Specific heat capacity of a material is the amount of energy required to raise the temperature of that particular material, one unit mass of that particular material by 1 degree. This is option B. So this specific heat capacity shows the material's ability to store the thermal energy and how it influences the temperature change due to heat transfer. Moving on to next question. Next question is, how is enthalpy related to Indian energy and pressure in the energy balance equation? So basic question from thermodynamics. What's the relation between enthalpy, internal energy and pressure? Our answer is H is equal to U plus P. Grossly, we can write enthalpy as sum of internal energy plus pressure energy times. Moving on to next question. Say number two problem. Consider a steady state flow of air having specific heat capacity 1 kilojoule per kilogram Kelvin with a mass flow rate of 1 kilogram per second and inlet temperature of 300 Kelvin. If the heat addition rate from the source is 2 kilowatt, what is the outlet temperature assuming no heat loss through the boundaries and negligible viscous dissipation? I'll try to compute the problem. So our answer is for a system we have net flow 1 kilogram per second and 300 Kelvin. Then Q into the system is 2 kilowatt. So we have to find outlet temperature. So the heat brought in by the system that so this can be obtained by MCP delta T or T plus 2 will give the output. So our option will be option A, 302 Kelvin. So 302 Kelvin. You can plug in the values and solve in this equation. Next question. Which of the following represents a valid Dirichlet boundary condition for the energy balance equation? Options are specifying the heat flux at a boundary. Option B, specifying the temperature gradient at a boundary. Option C, specifying the total heat transfer rate at a boundary. Option D, specifying the internal energy at a boundary. So which among the following will represent a valid Dirichlet boundary condition for energy balance equation? The answer is option A, specifying a heat flux boundary condition at a boundary. Here, heat flux as in terms of uh, watt per meter square, that kind of heat flux per area. So all other is gradients. Here, this heat flux as in terms of the rate of heat, the energy, uh, energy transfer per unit area at boundary. This can be taken considered as a Dirichlet boundary condition. Moving on to next question. How does turbulence affect the energy balance equation in CFD simulations? Question is on turbulence on energy balance equations. Options are: it requires an additional source time for turbulent kinetic energy dissipation. Option B, it modifies the thermal conductivity to account for enhanced heat transfer. Option C, it introduces an additional radiation times due to fluctuating temperatures. Option D, it has no significant impact on energy balance principles. You can inbox your answers. Our answer is option A. It requires to address the turbulence effect. It requires additional times to uh, address the turbulent kinetic energy dissipation. So these additional turbulent kinetic energy dissipation terms will be added as source terms in our equations. Okay, a small short break, 2 to 3 minutes break. I'll be back. So the next question is, in the energy balance equation, what does the convective term represent? So which of the following does the convective term represent in energy balance equation? Options are rate of heat generation due to internal sources within the control volume. Option B, rate of heat transfer due to temperature gradients within the fluid. Option C, rate of heat transfer due to thermal conductivity across the boundaries. Option D, rate of work done by the fluid on its surroundings. Inbox your answers. The convective term in the energy equation represents the rate of heat transfer due to temperature gradients within the fluid. Convective term represents how, as discussed before, how the fluid velocity is convecting or carrying the thermal energy. So best suited answer is option B. Next question. What physical property mainly influences the thermal conductivity in energy balance equation? Options are option A, fluid viscosity, fluid density, fluid specific heat. Option D, fluid thermal diffusivity. So, which of the following physical property mainly influences thermal conductivity in the energy balance equation? Viscosity, density, fluid specific heat, and thermal diffusivity. You can input your answers. The answer is option D, fluid diffusivity. So, density, heat capacity, all the terms are clubbed as uh, thermal diffusivity for energy equation for ease of uh, manipulating the term energy equation. So, the term thermal diffusivity has density and specific heat, which determines the rate of heat conduction through the fluid. Moving on to next question. How does the energy balance equation differ for incompressible and compressible flows? Options are: the viscous dissipation term is neglected in incompressible flows. Option B, the source term can include additional terms of pressure work in compressible flows. Option C, the thermal conductivity term is modified for compressible flows due to variable density. Option D, the equation remains identical with only property values changing. So the question is there any change in energy balance equation for incompressible and compressible equation and how it changes? Options are: viscous dissipation term is neglected in incompressible flows. Option B, source term can include additional terms for pressure work in compressible flows. Option C, thermal conductivity term is modified for compressible flows due to variable density. Option D, the equations remain identical with only the property values changing. Here our answer is option B. The source term include additional term for additional terms for pressure works in terms of compressible flows. Moving on to next question. In the energy balance equation, the convection term represents which of the following? Options are, the same question was asked before with another set of options. Options are uh, option A, heat transfer due to temperature differences. Option B, internal energy change due to pressure changes. Option C, energy transfer due to fluid motion. Option D, energy generation due to chemical reaction. The answer is option C, energy transfer due to fluid motion. Next question. The source term in energy balance equation can represent which of the following? Options are only heat generation due to internal sources. Option B, only heat transfer due to external sources. Option C, both heat generation and transfer due to various sources. Option D, none of the above. So the question is on source term of the energy balance equation. Which of the following can be represented using source term of a energy balance equation? The answer is option C, both heat generation and transfer due to various sources. Source terms can include uh, uh, different heat generation sources like joule heating and viscous dissipation, and also external sources like radiation or heat transfer through boundaries. So, source time in energy transfer can represent uh, various sources. Heat transfer and generation due to various sources. Next question is on well posedness of a system. Which property is not essential for a CFD problem to be well posed? So the question is on the a property of the CFD problem called well posedness. So options are existence of option A, existence of a unique solution. Option B, continuous dependence of the solution on initial and boundary conditions. Option C, finite solution at all points in the domain. Option D, compatibility of governing equation with boundary conditions. So, well posedness of a system or CFD equation or mathematical problem is on the is the ability or is the problem to have an unique solution which is continuously dependent on the initial and boundary condition. So these option A and B is the most essential properties of well posedness, and option D is uh, a by a section of option B, that is called dependence on the of the solution on initial and boundary condition uh, creates the compatibility of governing equation with the boundary conditions. So our answer is option C. This is not a essential property related to well posedness. So even though it is desirable to have a finite solution at all points of the domain, but it is not directly related to well posedness, whereas it is related to another property called boundedness of the solution, where uh, the where um, uh, the which property mandates the solution to have at all points in the domains and should be bounded by the boundary values. Next question. Consider the one-dimensional advection equation given by dou u by dou t plus c times dou u by dou x is equal to 0 for the problem to be well posed in the subsonic case where c greater than 0. The boundary condition at the inflow x is equal to 0 must specify which of the following. Options are only u, option B only dou u by dou x, option C both u and dou u by dou x, option D neither u nor dou u by dou x. So the question is on well posedness of 1D advection equation for a subsonic case. Which of the following is a must? Option A, only U. Option B, only dou U by dou X. Option C, both U and dou U by dou X. Option D, neither U nor dou U by dou X. Our answer is option A, only U. For a subsonic case, and for an advection case, we only need to specify only U at the inlet to have well posedness. Next question. In a CFD simulation of incompressible flow, which of the following is not a crucial aspect for ensuring well posedness? Options are option A, satisfying the continuity equation. Option B, imposing appropriate pressure boundary conditions. Option C, using a conservative discretization scheme. Option D, employing a time stepping scheme with CFL stability, where CFL is the current number criteria, that is current Friedrich-Lewis stability criteria. So the question is on for an incompressible flow, which is not a crucial aspect for ensuring the well posedness of the system. The answer is option D, employing a time stepping scheme with CFL stability. So time stepping scheme with CFL stability is for convergence and divergence scheme. I mean, to adjust the convergence. So for the well posedness of the problem, it is not CFL stability is not directly related. Next question. Consider a steady diffusion equation given as del square u is equal to 0 for a bounded solution in a square domain with homogeneous Newman boundary conditions dou u by dou n on all sides. Which of the following additional constraint is needed for well posedness? Options are: option A, specify a unique reference value for u within the domain. Option B, impose a specific integral constraint on the solution. Option C, neither A nor B. So for this particular problem in a square domain, whereas boundary conditions on all sides is given by dou u by dou n is equal to 0. So this dou n will be replaced by x and y according to the boundary spaces. So for the system to become well posedness, which of the following additional constraint to be needed? So well posedness is the existence of a solution and the continuous relation of that solution with the initial and boundary conditions. So for this problem to have a unique solution, which of the following additional constraints should be needed? So to answer the particular problem, we need a unique reference for u within the domain. So our answer is option A. To for the problem to have a unique solution, we need any reference value since all the boundary conditions are in gradient, that is dou u by dou n. So we need a unique reference value for u within the domain. So answer is option A. Because if there is no unique value within the system, within the domain, then we can't have a unique solution. Uh, so it will keep on changing. So it will violate the condition of well posedness. Moving on to next question. For a well-posed CFD problem, the discretization scheme should ideally be which of the following? Options are option A, explicit and computationally efficient. Option B, implicit and unconditionally stable. Option C, high order, accurate and conservative. Option D, all of the above. So the question is on, for a well-posed CFD problem, how the discretization scheme should be. Options are explicit and computationally efficient. Option B, implicit and unconditionally stable. Option C, higher order accurate and conservative. Option D, all of the above. So the answer is all of the above. Option D. So basically, our well-posedness only says the solution to have a unique solution, and the solution should be uh, respect the initial and boundary conditions. Moving on to next question. You are discretizing the Navier-Stokes equation using finite elements. Which of the following factors can affect the well-posedness of your solution? So when discretizing Navier-Stokes equation using finite elements, which of the following factors can affect the well-posedness of your solution? Options are choice of element type. Option B, mesh quality. Option C, order of accuracy and discretization scheme. Option D, all of the above. The question is on how or which of the factors can affect the well-posedness of your solution. So from the choices, all of the above, that is choice of element type, mesh quality, and order of the accuracy of the selected discretization scheme, all the all these factors will affect the well-posedness of your solution. So well-posedness is saying to have an exact solution to having a solution, unique solution, and that unique solution will be dependent on all of these factors. So our answer is option D, all of the above. So that's all for today. Thank you for joining. Thank you for joining. ഇറങ്ങി പോടെ ഇറക്കാ ചുമ്മാ ഐ ഐ ടി മദ്രാസിൽ അതിനൊരുത്തൻ കയറി നിന്നിട്ട് മനുഷ്യനെ ഉറപ്പിക്കാൻ വേണ്ടി